Today, we have the pleasure to have Professor Segurado, who is going to give a talk about fast Fourier transform-based simulations for capturing microstructure effect on the mechanical response of metals. So I think it's going to be a really interesting topic. And regarding the dynamics of the webinar, it is expected to last for an hour, and we will have around 45 minutes of presentation, and then we will have some time for questions. So please write them in the chat, and at the end of the webinar, we will ask the questions to Professor Segurado. And if it runs late, more than 1 hour, and you have to run away, don't worry, because we always upload these webinars to YouTube. So in any case, we will ask the questions anyway, and you will have the chance to see the responses later on. So with no further delay, I would like to introduce Professor Segurado. He graduated in materials engineering at the Technical University of Madrid in 1999 and got his PhD in the same university in the year 2004. From 2008 to 2019, he was an associate professor, and in 2020 he obtained a full professor position in solid mechanics at the UPM. Additionally, since 2008, he holds a double appointment as researcher at the India Materials Institute, where he leads the multi-scale materials modeling group. He is the coordinator of the Integrated Computational Materials Engineering research program of the Institute, which groups 6 research teams of India. Professor Segurado is a Fulbright scholar, and he has held visiting positions at UCLA, Los Alamos National Laboratory in the US, the Technical University of Wien in Austria, and MC Master University in Canada. He is author of more than 90 international papers in the field of computational solid mechanics and has more than 3,800 citations and an H index of 32. He has participated in more than 40 research projects with international, European, and national funding, being principal investigator of 8 of them, including FETOPE and Clean Sky European projects. He has been included in the last year list of the 2% scientists in the world developed by the University of Stanford. So, with no more ado, Professor Segurado, the floor is yours.
Okay, thank you very much for the introduction. Let me try to share the presentation and let me make us full screen. Are you seeing the presentation correctly?
Yes, perfect.
Okay. Okay.
I don't know if you can go to full screen mode or something like this.
I'm in full screen mode. You don't
Okay.
see it in full screen?
We'll see the Zoom and all these PDF options.
Okay, let me try. Still, you see the menus or only the presentation?
I see both, but I guess that...
Well, 1 second, then I will do other thing. Stop sharing, share screen. I will set my full screen. I will go here and then I will show. last chance. Okay. Now it works or still see the same?
Now it works.
Okay, so sorry for this small delay. Thanks first to everybody for attending the webinar. I see some familiar names, so hi to everybody that I know, and thanks for coming. So as Eduardo has introduced, I have prepared this talk entitled FFT-based simulation for capturing microstructure effect on the mechanical response of material, trying to give an overview of different things that we have been doing these last 4 years in this topic. So I will first make a small introduction and motivation of the work. I will present the framework in which we will be working, and then I will show 3 different examples, okay, that I will explain later, and then I will finish with some conclusions. Okay, what is the motivation? So everybody knows that there is a strong influence of the microstructure in the mechanical behavior of any material, but it also happens in mechanic materials. When we're speaking here about microstructure, we're speaking about different things depending on the length scale. We can speak about the nanoscale, and then microstructure at the subgrain scale means the initial dislocation density. We have precipitates at the nanoscale, the size, orientation, shape of the precipitates, and these things. And with this will determine the strength of the crystal. But we can also refer to microscale at the microscale. So we don't see these sub-micron defects, but we see a polycrystalline nanostructure. And in this case, the microstructure is the polycrystals that is forming the microstructure. So it means the grain size, shape, and orientation distribution. And this will strongly influence the response of the alloy. And finally, at the mesoscale, okay, we don't see the grains, but we can have larger particles, or we can have even a particle rain for metal, okay, and these second particles that are big enough will also affect the strength and ductility of the alloy. So being said that, it's clear that having models and simulation tools that allow us to estimate the macroscopic response as a function of this microstructure at any of this level is fundamental. For science, it's clear, but also for industry. And I put here some examples, and I see some faces that this is not just pure science. So we have projects, and we have been working with people in Airbus, in MSc Extreme, and in ITP Aero, okay, that want to use or to implement these tools for the day-to-day work in the finding materials or optimizing the design. Okay, so as I told you, these models are important because they will help to optimize the design of a part. So if I design taking into account the microstructure, I can do better. I can have smaller thicknesses, and I can find more optimal designs. But I can also have a guide to develop new materials and to infer in the processing to get optimal microstructure. And the main tool here is what we call computational mobilization. Computational mobilization aims at obtaining the mechanical behavior of a point. Here we have a full test, a full specimen, and then we focus on a point, and to obtain the stress-strain response of that point, what we do is to have a box where we represent the microstructure. We call this box representative volume element, okay, and we put there all the microstructure information that we have from the experiment. So grain size, shape, and orientation distribution, second phases, and we also put models that account the behavior of the phases, grains that are present there. That can be simple things like elasticity to very complex things like strain gradient plasticity with some regular damage and something like that. And what are the scientific keys here? What are the challenges? Well, the 2 challenges is first finding adequate constitutive equations that are able to describe the underlying physics of the phases, including accounting for size effects. And the second challenge is use of realistic RVEs. Realistic RVEs mean very detailed and that statistically represent the microstructure. So the first challenge is classic in micromechanics. So in the last 40 or 50 years, we have been developing constitutive equations to account with more and more detail what happens in the materials at the micro scale. So we have the crystal plasticity model, strain gradient plasticity, regularized damage, more and more things. And respect to the second challenge, classically we have been using finite elements for everything, but I would say that in the last 30 years, in the search of more efficient computational models to solve this problem, FFT-based homogenization has started to be a very interesting technique, and it's started to be widely used. Okay, so in this talk, what I want first is to introduce this technique. So what is FFT homogenization? Very briefly, with almost no equations, but which are the capabilities. And then I will show 3 examples in which we have been working that shows what is the potential, what we can do with these tools to link the microstructure with the macroscopic response. These 3 examples will be first at the monotonic response, quasi-static response, so how we can obtain the stress strain response of polycrystals, but taking into account grain size distribution, so including what we call size effect. Okay, the second thing is how we can use these tools to predict fatigue life and nucleation, and the third thing is how can we use these tools to predict damage. In this case, I'm focusing at a larger scale, so in a metal matrix composite. Okay, let's start first with the general framework. The FFT homogenization, it's something that was initially proposed in the mid-90s by Hervé Moulinex and Pierre Souquet, and but it's based on things that have been used in other areas, and they are quite common. The first thing is that we can use if we have a function, we can transform the function in the Fourier space and compute a derivative very easily. So we convert derivatives in multiplication. And the second thing is that a common operation in mathematics that is called a convolution of 2 functions can also be done very efficiently in Fourier space. So we just have to multiply the transform of this function. With these 2 ingredients, okay, we can solve boundary value periodic problems on RBEs, okay, by something that is called the Green's function. So this in convolution, that is this property, and Green's function that are obtained with this property. So we can solve the same thing that we solve in finite element, but using this Fourier transform. The key here is that the algorithm for doing this transformation from the real to the Fourier space are done with the fast Fourier transform algorithm that is super fast. And this is what is behind the efficiency of this method. Okay, and as I told you, why this instead of FEM, what are the reasons in the case of homogenization? And they are, from my viewpoint, 3 main reasons. The first one is the periodicity. So in homogenization, we normally want to use RBEs that are periodic, and this is for free in FFT. And on the contrary, in FEM, we have to impose it apart. Second is the computational cost. The computational cost in FFT grows n log n, and this is in general much more efficient than in FEM, that depending on the type of solver, we could go to n to the cube, 2n to the square, 2n to the cube. So it's more efficient, what means we can go to larger number of elements. So, and the third thing is that we don't require meshing, so we can use directly images or tomographic data. This is an example. This is a tomographic image of a lattice material that we have directly plugged in our code and solve it. Okay, so I speak about my code or our code because we have a code developed here at INDEA. It has been mainly developed by Sergio Lucarini, that is a former PhD that's now in Imperial College, and myself. And well, it's another FFT code. There are several. It has several schemes implemented. What is maybe interesting, that's the reason why we develop it, is that we want to keep the compatibility with all the work that we have done before in finite elements. So we built a wrapper so we can use any Abacus UMAT developed for solving problems in Abacus, even at the macro scale, and plug it into our code in FFT-MAT. So then it's absolutely open and general. It's not for metals, what I'm telling here, but we have used it for lattice materials of polymers and anything. So it's parallelized, it includes several models, and it's licensed as open source. So if you're a researcher and you're interested, you can just write us from there is a link in the webpage of INDEA, and you can ask for it. Okay, so, and what's the problem we want to solve? The problem we want to solve, we have an RVE. Here is an example with different phases. Okay, and we impose an macroscopic deformation history. Here, we call it the deformation gradient history. That is like the strain. Okay, so we have the macroscopic strain, and we want to find the microscopic fields. These microscopic fields are stressed as a strain at every point. So, we know that the macroscopic applied strain, it's just the average of the microscopic strain, the same in terms of deformation gradients, okay? This is the Hill-Mandel, okay, this is the Hill-Mandel statement that is fulfilled here due to the periodicity. And the problem is then we want to find the stress fields that are in equilibrium such that the strain at every point fulfills the homogenization, where these F that are the fluctuations are periodic, the same thing on the left and on the right, okay, and that the deformation gradient is compatible. So there are many algorithms in FFT. We use mainly the Fourier-Galerkin approach using mixed control that we developed in this paper. The approach was developed by other people, and it's a very clever approach. And this is what is behind most of the examples. I'm not going to tell anything of the equations because I think it's not the place, but you can find in those papers all the information, okay? So I will just go to the applications, okay? We will start first in how we can use these models to study the monotonic response of polycrystalline materials. Let's start first then with the ingredients. So if it's polycrystalline materials, we're speaking about computational polycrystalline homogenization, okay? And in this case, we have the two ingredients. One is the microstructure and the other one is the constitutive behavior of the phases. In terms of the microstructure, if we want to study a polycrystal, what we need is the distribution of grain size, shapes, and orientation. In this picture, what you have here is the pole figures. That's telling me the texture. So this is the orientation distribution. We can get it from EBSD or from any type of diffraction technique. What you have here in the graph is the grain size distribution. So in this case, it's a log normal, and we can get also from experimental images, okay? And it's telling which is the distribution of grain sizes. And what you have on the left is if we take this information, and we know how equiaxial are the grains, we can build this type of representative volume element. This is a very huge RVE that contains tens of thousands of grains, but something that is doable within FFT. Okay, this is the microstructure, the RVE. The second thing is the constitutive equation. If we're doing polycrystalline homogenization, the constitutive equation is the one that applies to a grain. And this grain behaves an elastoviscoplastic material, and it's absolutely anisotropic depending on the lattice and the orientation. And this is well represented by the crystal plasticity model. Okay, here I put a reference on a review that we wrote 3 years ago, where we include all the models and techniques for computational homogenization of polycrystals. Okay, so then let's go to the crystal plasticity model very briefly. The crystal plasticity model, as I told, is just aiming at describing the plastic deformation of metallic single crystals that is the result of crystallographic slip. So it means that one part of the crystal slip respect to the other thanks to the movement of dislocation. The model was proposed almost 100 years ago by Taylor and Elam in the 20s. Okay, although of course what we have right now has evolved a bit from that moment, but the original idea of these shears depending on some resolved stress and how this is accommodated from a single crystal to a polycrystal comes from these ages. So the main ingredients of any crystal plasticity model are specified here. The first thing is that we consider two configurations. So this is the material with the lattice, you see it here, and we consider that for deforming the material, we have two types of deformation. One is called the plastic deformation, that is this configuration, where we only consider the deformation due to a slip. So there are some direction, S, and some plane, M, in which we have a shear from one part of the crystal to the other, and this is represented here. So we have a change of shape, but we don't have volumetric deformation, and the lattice, that is more important, has not changed. That is why we keep this square. And then we have a second or a final configuration in which we add the change of the distortion of the lattice. The distortion is an elastic distortion. The atoms move from the equilibrium, so that's why you see this original lattice distorted. So the final configuration is this one, is the only one that we see physically, but this decomposition is very useful because then we can model this part separately. What we say is that this part that is only the pure plastic deformation, so it's a velocity rate, so the strain rate of this is just the sum of some shear rates, so some shear deformation in some planes and directions. Alpha are these planes and directions and are what we call the slip system. So they are characteristic of the lattice we're using. In FCC, they are the octaedrical system. So alpha goes from 1 to 12 and are all these systems. Okay, so this is the kinematics. So we have to go now to the constitutive part. The first thing that we do is to say that, of course, the stress is due only to the elastic strain that is written here with a fine strain language. And the second thing, we have to define a driving force for this slip. The driving force is what we call the resolved shear stress. That is this equation that is usually simplified to a projection of some stress measure in the mid configuration, like the second Piola-Kirchhoff, but it's just thinking it's that is projecting the stress in a plane and in a direction. Okay, so this is an scalar, and then we define this scalar slip rate on this system just depending on the driving force, that is tau, and some internal parameters that are g and k. G is the one that corresponds to critical resolved shear strain, and it's explaining the isotropic hardening. And k, it's what we call a back stress, and it's incorporating the kinematic hardening. So we can modify this law, and with this we will have different models, as I will show, but all the main items of any model are here. Okay, so the first application, it's just obtain stress strain curves, but trying to reproduce something that we find in experiment. In experiments, we find a law that scales the strength of polycrystal with the size of the grain. This law is normally it's fitted to a Hall-Petch relation, okay, that follows this, and is that the strength is inversionally proportional to the square root of the grain size. Okay, this work. So this law works pretty well, okay, but it's pretty phenomenological. What is the origin? Is universal. There are other microstructural features that depend on here, and the most important thing for us: can we use computational mobilization to predict this Hall-Petch effect? So what I'm showing here is this work that we published on JMPS, where we try to apply crystal plasticity in FFT homogenization, some special kind of crystal plasticity, to answer some of these questions. Okay, what is the physical origin of size effect? So the physical origin is the accumulation, or well, it's more or less well accepted, that is the accumulation of of geometrically necessary dislocations around grain boundaries. So dislocation, when they slip, they find the grain boundary and they pile up there. Okay, what they pile up there, they form a pile up, and this increases strength. Okay, so the size effect that this piling up is forming depends not only on the grain size, but on things like the lattice itself, the anisotropy, the texture, initial dislocation density. So just putting an universal law like Hall-Petch, it's a very, very strong simplification. So the idea is, well, don't use just the Hall-Petch. Let's try to obtain the relation from virtual testing, and this is what we are going to do. Okay, so now the particularization of the crystal plasticity model is this shear rate is a power law, very simple. So it starts to shear when the resolved stress reaches the critical resolved stress. Second ingredient, we're going to say that the critical resolved stress, the one that marks the starting of the shearing, okay, is given by the Taylor model. And the Taylor model is just saying that it's proportional to the square root of the dislocation density. And we're going to establish that we have two types of dislocation densities, the SSTs, that are the dislocations that are more randomly in the material, okay, and the GNDs. And the GNDs are those dislocations, okay, that are not equilibrated, okay, and that are the ones that more or less we can say form the pileups. Okay, the evolution of the SSTs follows this ordinary differential equation, that is the Cox-Mecking law. We have creation and annihilation, but this second part, the GNDs, is something purely geometrical, because these GNDs, what they make in the crystal is to cause like type of curvature. Okay, so this curvature can be very well expressed by the Knight tensor, and this Knight tensor can be obtained by just computing the curl of the deformation gradient, of the plastic deformation gradient, the one that we have in this mid configuration. So if we can measure this from the FFT simulation at this field, okay, then we can obtain as a result the density of GNDs. We can put it back in this equation and we have the hardening effect. We can do everything within the FFT code, and then we are trying it. So we use different materials, copper, aluminum, nickel, and silver, all FCCs with different grain sizes and RVs of this type. And first we check in the model what is the initial dislocation density. No GNDs, just pure statistically stored dislocation. And we see that the model predicts a dependency on the yield on the density of dislocation, what is correct. And the second thing that we see is that we have here different grain sizes, and we see the type of effect that we see in Hall-Petz. Okay, that is, the smaller the grain, the harder or the stronger the material. Okay, so here we are combining two items, not like in Hall-Petz, because in our model we can plug which is the initial dislocation density in addition to the grain size. Okay. Where do the GNDs appear? Where we have this curl of FP? Well, it's mainly near the grain boundaries where we have the plastic incompatibility. So one grain wants to deform in one direction and the other in another direction, and then these GNDs appear to make this compatible. And what type of equation we can fit? So the thing is that it's a bit more complex than Hall-Petz. We find that this type of equations that are also universal. So Hall-Petz is very old, so all the people know that this is the correct scaling. So we have something like an exponent that is not 0.5, it's a bit bigger, okay, and scaling that depends on the grain size, but also on the square root of the initial dislocation density. Depending on the lattice and on the material, copper or aluminum, the model works better or worse respect to this equation and respect to experimental values. In aluminum, it works perfectly. Okay, in copper, it works differently, and this is due to the storage of dislocation that is not explicitly treated here. Okay, but the model is able to predict for the same metal and fitting with other metals many cases. Okay, what is the effect of grain size? But what is important here is that we're not using a very simple phenomenological law. No, we are putting the real microstructure. So we are considering the actual texture, and we're putting the actual grain misorientation and grain size distribution, not only the average. So it's much more general than what we do for Hall-Petz. Okay, the second example I have to run a bit is fatigue. So we can use these tools for predicting fatigue life nucleation. So it's well known that fatigue nucleation depends on the polycrystalline microstructure. So the grain size distribution and so on. How? Well, we form somehow localization of a strain. Here is an experiment. Here is an FFT simulation. You can see how when we have a twin band, for example, deformation localizes there, and this localization cycle by cycle start to degrade the material and somehow nucleates a crack. Okay, so we need models that take this into account. From a modeling viewpoint, this is the same image. You have a polycrystal, you cycle, and you find that the plastic, so the shear rates are located and on some preferential sites in some preferential orientations. Okay, sorry for this. Okay, and this is what we want to try to see here, and we're going to follow a strategy of what we call microstructure sensitive fatigue life prediction. Okay, the idea is that we're going to use FFT simulations, okay, to correlate fatigue. So we are not breaking the material, we're just estimating the cycles that we need to create a crack. So first, we generate RVEs that are representative of the actual microstructure, step one. Second, we are going to calibrate the crystal plasticity model. That takes into account the cyclic response. Is a bit different to the one that I have shown. I will show you now. Third thing, okay, we're going to simulate the cyclic response, so the full field simulation for several cycles, 3, 4, 10, until we reach what is the stable hysteresis cycle. And when we have this, the fourth step is we're going to extract to post-process the result to get some fatigue indicator parameters. So the aim is then finding a very simple phenomenological law that if I have these fatigue indicator parameters, when the law is fit, is able to give me the number of cycles that this will survive. So the larger the FIP, the smaller the number of cycles. This work has been mainly published in these 3 papers. We have other 2 ones, but this is the main work, okay, and the part of FFT in these last works. Okay, so more details, you can find it there. What is the fatigue indicator parameters? There are several proposed in the literature. We're focusing in the dissipated energy, or the people, instead of dissipated, they are focusing on the stored energy. The idea is the dissipated energy per cycle, okay, is going to each point and see which is the energy, okay, dissipated on each slip system. So this is a map, because it depends on the point. From this map, we can then integrate in small bands that are parallel to the slip systems for every grain and obtain the maximum of this integral in all the band of the RV. That is what we call, that is the representative fatigue indicator parameter for all these RVE. Okay, and then if we have that, we can predict life, and this is good, and we have this type of predictions. This is very interesting, but some statistic is missing here. And not only some statistic, if we follow this, you can think that if we use a much larger RV, okay, then the probability of having a very bad oriented grain increases. So the problem of the deterministic way of doing this is that is strongly depending on the RV size. That is artificial, because the RV is something that we choose. Okay, you can see here in the grain, this is the probability of fatigue indicator parameter to occur. The same simulation, just changing the RV size, the probability moves to the right. So it means that the life prediction of this small or this big RV will change. Okay, so what we want to do is just to get rid of RVE effect, okay, using some extrapolation methods. So the key is, let's, instead of having a single RV, we're going to use 100 of them, what we call a statistical volume element, okay? And then we're going to obtain the value of each of those, okay, in order to generate a probability distribution for all this set. Okay, and now the thing is, if instead of having this set of RVs very small, we have bigger RVs, then the probability of finding a critical grain, okay, is more probable in the bigger one, and depends on the ratio of volume. So what we can express here is the cumulative distribution function of failure or of finding a critical grain in a big volume V1, that is m times a smaller volume V0, is nothing but the power, okay, of the original probability distribution. So if we follow this very simple thing, okay, then what we can do is just trying to improve the other results. So we are going to use a set of RVs, smaller, okay, and then we are going to generate, once fitted, the fatigue life, okay, not as a point, but as a probability. So I'm going to explain these graphs because I have gone very fast. These are experiments. Here is the applied strain, and here is the number of cycles of surveillance, okay? So, of course, the smaller the applied strain, the longer the life, okay? And this is the type of experimental trend. What we are doing here is we are fitting some of this value, maybe 1 or 2, for this law, and then we are now predicting this probability distribution. So what we are giving as output is not only the fatigue life for this strain, but also the probability of having a fatigue life, okay? What is interesting in this prediction, I'm going to emphasize, is that it's absolutely multi-axial and general. It means I fit the crystal plasticity law with a single experiment, and I take maybe 2 fatigue experiments to fix some of the points. But now, if I take my RV and instead of applying a uniaxial cyclic history, I have a multi-axial cyclic history or different type of cycles, then I can still do the same. So I can get the fatigue indicator parameter distribution, I can make the statistical study, and I can provide life. So the model is expensive because it requires FFT simulations of many cells, but it's absolutely general. So I only fit a general curve based on FPI, so I'm extending the thing to multi-axial fatigue and fatigue with different shape of the cycles in terms of the time and so on. Okay, good. So what is another win of this statistical model? The other thing is that, as I told you, there is a size effect, and the model takes into account the size effect. This is an example. This was an experiment, and for one particular case, for a given applied strain, okay, we have that the life is this red column. Okay, now with the model, with a very simple equation, that is the Gamble equation that I have shown, we can predict what would be the life, okay, of a very big part, okay, made from this material, that the life would be this one, or the life of a very small specimen that would be something like this one. And this is something that the industry observes. So what we can see in the industry is that whenever we compute fatigue of a big component, we cannot use directly the results of the test. We have to do some degrading, okay? And this model allows us to know which factor we have to apply from going to the experiment to the real part, okay? Just in based on Bible or Gamble theory of statistics, and it works pretty well. Okay, good. Now I'm going to the last example, that is how can we use this type of homogenization techniques to study damage. Now we're going to jump a bit because we are not going to consider the grains, just a metal that is homogeneous. So we are at a larger length scale, but it's a metal in which we have precipitates or big particles. So it can be considered a metal with precipitates, or it can be considered as a particle reinforced metal. Okay, nevertheless, it is well known that we have microstructure influence in the result, but we have seen that it happens at the monotonic, and it happens also in the cyclic response, but it also affects the fracture, the static fracture. Okay, in the case of a pure polycrystal, we can see that the grain size in this graph has an influence in the ductility. Okay, and in the case of metal matrix composite, even if we have the same volume fraction of precipitate, the size of the particles has an influence in the ductility. So again, it's fundamental to understand this, and this goes beyond what we have seen up to now. So again, FFT solvers are our tool, but because we're speaking about fracture and failure, some of the tools that we have in finite elements cannot be directly adapted here. For example, XFEM or cohesive elements that rely on element phases cannot be applied here. So what can we apply here? the best thing are continuum damage and phase field fracture, because they don't rely on the finite element itself. They rely on a PDE. So that's something we can adapt great to FFT. Okay, the second option, that's phase field fracture, is very interesting, and some recent papers in the last 3 years have used FFT for phase field fracture, and we have also incorporated in our code. But because we're interested in ductile failure, we are more interested in what we call continuum damage mechanics. So what we want to do, okay, we will do a phenomenological plasticity model, so standard von Mises plasticity, not crystal plasticity, and we're going to incorporate ductile damage mechanics, but doing something that is called non-local regularization or gradient model, okay, and having this ingredient, we will be able to incorporate size effect, so particle size effect in the failure, in the ductile failure prediction of this material. So this work has been published in this paper of computer methods in applied mechanics, and this one that is in the final review in JMPS. Okay, and this will be this is a summary of what we have done. Okay, what is behind? Behind we have a continuum damage model, and if you are familiar with continuum damage mechanics, you have for sure heard about the Gerson model or the GTN model. The Gerson model is a plasticity model that, in addition to standard plasticity, takes into account the evolution of porosity. So the material does not only plastify, but due to the plastic strain, if we have some porosity, this porosity grows, so the volume fraction of pores grow. Okay, so what we have is a yield function. So this is just pure von Mises, J2, and it adds some terms, and the terms depend on the porosity F. So when F increases, the yield locus gets smaller and smaller, so the load carrying capacity of the material decreases, okay? And we have the yield, okay, but we need also some ingredients to see how this volume fraction of porosity evolves, and we have in the original model 2 ingredients. One is nucleation, so we have smaller, non-visible to this length scale precipitates or grain boundaries that produce the nucleation of porosity, is this part, and we also have growth, okay? So if we have an initial void, the plastic deformation around the void is does not produce changes of volume, but itself it accommodates the change of the size of the void. So it's just saying that the volumetric part of the plastic deformation, okay, that in a standard model, it's 0 in standard plasticity, here is accounting for the void growth, okay? Well, it's very fast to explain this model, but this is the idea. And if we put it in an FFT or FEM solver and we study stress strain, we find what we call a localization problem. So the smaller the mesh, the deformation will be localized in very small regions, okay? The size of the region depends on the mesh. So this is mesh dependent, and this is terrible. What can we do to improve this? We can use a non-local model, and among the non-local model, we're using the gradient approach. The idea of a non-local model is saying, okay, the volume fraction of porosity is not something that depends only on what happens on that point. It depends on what happens on the points nearby. And what happens on the points nearby have to be defined and can be easily defined by an integral, but we can transform this integral of the nearby points in a in something depending on the gradient, okay? This is the equation, and this equation is saying, imagine that alpha is the porosity or any local state of the material. It can be the plastic strain or the porosity or whatever. What we're obtaining with this equation, it's like a non-local version, so an average version. And this average version is a solution of this partial differential equation. So input is alpha, output is alpha averaged, and this L is the characteristic length. The characteristic length means which is the influence of the nearby points. If L tends to 0, we recover the original model, size dependent. But if L is a physical length related to the distance between nanoporosity and things like that, then what we are getting is that the formation now localizes in bands, and the bands will be of size L. So we are not anymore depending on the element or voxel size. We are depending on a physical parameter that is this L. Okay, so at the end, from the mathematical viewpoint, we have a couple system of PDEs. We have the standard equation alpha, and we have one of these Helmholtz equation for each of the variables that we are making non-local. Okay, and this can be solved in a staggered manner within FFT. Again, I'm not going to the details, but to the results, and let's see what is the effect. So if we go to a very simplistic two-dimensional framework of a particle rainfall composite, elastic particle within a matrix, what we see with the local model is localization. Okay, you see that when we make smaller and smaller the mesh, the result changes and the energy dissipated changes. That is not good. Okay, on the contrary, whenever we introduce this gradient regularization within FFT, we see that the size of the band, that is this, it's totally given by the characteristic length. So if we refine, the only thing that we get is a more accurate result, but macroscopically, the result is equivalent, okay? So energy is preserved, and this is what we wanted, okay? This is checked in 2D, and we can check it in 3D, but for a more complicated RVE. So for a real material reinforced with spherical particles, okay, and not only one, so not periodic, not only one in the middle, but a random arrangement of them. Okay, now let's apply some strain, some uniaxial strain in one direction, and let's see what we get. The first thing that we get is that we use, if we use in this framework, local plasticity, okay, local Gerson, sorry, we have a strong voxel size effect, as it happened in FE. On the contrary, whenever we have this gradient enhanced non-local version, all the curves superposed, and we have an energy dissipated that is independent on the discretization of the model. So this thing is good. And what we predict, so we can go here and we can now look at the micro scale and see how damage, in this case porosity, is distributed. What we see is that first, the distribution is independent on the discretization. That's great. So the shape of the bands where I accumulate damage is the same for very coarse discretization to very fine discretization. Okay, and what we see in this figure is that damage locates in bands in this model that forms 45 degrees with the loading direction. That is something that is expected. What else can we do? We can check which is the effect on the ductility on the particle size, and what we see is that the smaller the particle, smaller means d, okay, tending to 0, the more ductile. Okay, this is not true if we consider particle fracture, but it's true if we just consider matrix softening. That's happened, for example, at high temperature. The other thing that we can do with this model is to predict the size effect on the strength. Okay, so what is the difference in the strength of the material depending on the size of the particles? We do that including strain gradient plasticity, similar to what I presented at the beginning, together with this damage model, and we see that the smaller the particle, okay, D, smaller means L asterisk bigger, the smaller the particle, the stronger the material, similar to the Hall-Petch relation that we have. Okay, and we can see if this thing goes with the experiments, and it more or less, we can see that more or less it works. So we have taken an experiment with the same material having same volume fraction, but 2 different particle sizes, and we see that we can quite accurately predict the size effect on the particle first. And the second thing that we see is that if we don't use damage, we over predict. So when we use both ductile regularized damage plus strain gradient plasticity, we're able to predict accurately the effect of the particle size on the global response. Okay, so this is the conclusion. You can use quite efficiently gradient models, okay, in this framework, and we can further extend this to crystal plasticity. So I have more or less finished on time. Let me just recall what I have told in this webinar. What I have to show is that FFT homogenization, if combined with physically clever constitutive equations, okay, these equations might be complex, like strain gradient plasticity, or couple PDEs, like in the gradient ductile damage model. But if we use the correct physics and the correct mechanics, we have an extremely useful tool to predict the effect of microstructure in the mechanical response. And I have shown this for three cases. The first one is how we can incorporate grain size effect in a polycrystal, but taking account not only the grain size, but all the grain size distribution, orientation, just following this polycrystalline homogenization. The second example is, again, how we can predict fatigue, but predicting fatigue not with a very simple model, but with a simulation on FFT, okay, that allow us to include complex cases that are not easy to be predicted with phenomenological model, like multi-axial fatigue, fatigue with different cycles, etc. And the last example is that we can extend this to damage in order to see how ductile damage evolves and which is the effect of the size effect of the microstructure in the damage. I have chosen these three examples because they are representative, but we can do many more things, and we have been done in my group, but there are many other things. So we can study wave propagation, for example, in polycrystals, just to have and study about how we can study sound waves to predict some microstructure items like grain sizes. Okay, we can use these tools just to link the microstructure that we have after additive manufacturing with the material response. Okay, we can also extend this to study lattice metamaterials. Okay, so taking from tomography these nice foams or lattices and see which is the effect of porosity, and many other studies. So I stop here. I thank all of you for your patience and for being here. And now I'm open to questions.
Thank you, Javier. Very interesting, lots of information. And I'm sure that sooner or later we'll have to do a catch-up webinar in which you show how you apply all these methodologies to these three examples that you put at the end of your slide, especially in additive manufacturing, metamaterials, which are very, very hot topics right now. We have one question from the audience asking you if you try to apply your approach to BCC or BCC, HCP, or dual phase polycrystals or half-edge effect. We cannot hear you.
Okay, now yes.
Yes.
So, hi, Derek. Nice to see you. No, we haven't. We have just, we did this just for pure FCC. So we took examples for FCC. I'm not sure about what will happen in BCC. I'm pretty confident that in HCP it would be very similar, because in HCP, well, you have twinning if you just focus on sleep. So the type of response is quite similar. So you have an isotropy, but I mean the scaling is similar. In the case of BCC, you have other things happening. So I'm not sure how direct will be the extension. But the concept of GNDs appear in any lattice. So if you have incompatibility of the deformation between one grain or the other, okay, it means that some incompatible strains should appear that accommodate this difference. And then these incompatible strains at the micro scale are the presence of geometrically necessary dislocations. So somehow or other, with some adaptations, I think we could try this, and I think it would reasonably work.
Thanks. We have another question from Farsim Mosafari. He asks if the energy-based fatigue method is able to address negative R ratios.
Yes. I'm not sure in the examples what I have chosen it was a positive, but we have done with both. I think indeed, I remember I showed two curves. here. You see, one is the difference precisely I didn't explain. It's for different R radius. This is negative on the left and this is 0 on the right. So we have done it, and with the same, exactly with the same fit-in. So we have fit only on these points. We have predict all the other cases, and we have changed R, and it works in the two cases.
Great. We have another question asking, how can we apply this FFT technique to solve textile composites to predict the elastic properties?
Well, I work in composites some years ago, but I'm not active in composites right now. But I can tell there are many people in the FFT community working on composites, and I have seen incredible simulations of textile composites where they have direct images from tomography, or these microstructures developed artificially, but they reproduce all the entangling of the textile, and they are using these techniques to predict not only the elastic behavior, but even further nonlinear response. So the answer is yes, and you can do the same. You have just to model your RVE from experiments, or just by some type of artificial generation of the microstructure. You have to put the correct constitutive equation. In case of elasticity, super simple. Otherwise, you have to think what happens with the matrix, with the polymeric matrix, and just let it run. So it's general.
So I think we don't have any other question, but in any case,
I think there is one question.
Oh yes,
with
Q&A.
Hongyu. Well,
you're seeing it. Let me
yeah, I'm seeing it.
Read it out loud. So fundamentally, the FFT is also working with cylindrical coordinates or spherical coordinates.
Well, Hongyu, yes, I think yes, but I have to think how to. Well, I should think about it. So the Fourier transformation works with any coordinate. That's for sure. So the only thing that I'm thinking is in the shape of the RVE. Okay, so axisymmetric cylindrical coordinates and axisymmetric cells would work definitively, because it's what you're doing in FE when you have a surface. In the case of a spherical, so if you keep so if you have a spherical states or something like that, it might work, but I'm not sure.
We have another question asking if there is any open source code for FFT.
So
this comes from the person regarding the textile composites.
Okay, so they are I think many open source codes for FFT. You can put that in FFT homogenization in Google, and you will find them. Our code, all the results that have been shown here have been made with our own code that is called FFT-MAD, and it's open source for researchers. So if you just look at in their webpage and you want a version, you just have to sign a license that is for free, and you can try to adapt it to your problem. So, but there are other codes, and I think there are many codes in the literature, and you can try to find them.
Okay, we have two more questions. Can we do Eulerian type material flow calculations?
Yes, you can do Eulerian type calculations, for example, but you have it is not, well, of course, if you do, I think yes, and we have to think in the problem. I know people that are doing crystal plasticity in fine strains using a Eulerian formulation, just projecting it we to the original lattice. So what we're doing here is pure Lagrangian, and we use the initial configuration. But if you have velocities instead of displacement, you don't have any problem in principle to use Eulerian simulations, but periodicity and shape are important. So maybe this is a problem.
Okay, we have another one asking about if the FFT-based solver can model hot deformation flow behavior, then the behavior related to VRX.
Okay. Which what
it is in the Q&A. I don't know if you can read it yourself.
Okay, I see the question because I was in the other. Well, I think if you if you get the correct physics with a problem, yes. So in this case, high temperature means that the constitutive equations will change a bit. I'm not sure, but what I've shown most are elliptic equations. You can do hyperbolic equations, and that's something that we're doing for dynamic. You have to think that anything that you can solve in FE can be solved here if you are able to consider something that is periodic. And periodicity has problems because if you have periodicity, you cannot easily incorporate differences in the boundary or the Dirichlet boundary conditions and so on, and some problems need of that. Okay, so then, but in this case, I'm not particularly sure.
So Vicente Timon asked for intervening to ask a question. So Vicente, if you want. If not, we have another question from the chat asking, would there be much differences between finite strain and a small strain formulation of the model?
I'm sorry, I'm asking, so I didn't get it. So just finishing asking Amit, of course DRX can be done, but you have to link mechanics with some type of dynamic recrystallization approach based on the energy density. There is a work by Levenson doing that with his FFT code and some criteria. So of course it's perfectly doable. And okay, the other question that you were asking, sorry.
Would there be much differences between finite strain and a small strain formulation of the model?
Well, it depends on the physics of the problem. In the case of crystal plasticity, if we think in fatigue, none at all, because the fatigue strains that we normally apply, even in applied strains, not the stresses, are 0.001 or something like that, no difference. But if we think in the case of ductile failure, maybe yes. So it depends very much on the problem. Okay.
So I don't know if anybody else has any other question. I guess not. So I have put in the chat the link to where we have the information of the FFT math code developed in the group of Professor Segurado. So if any of you are interested in getting a license and trying it out for your research, please send us an email to the email address that appears on that website, or straight or directly to Javier Segurado, and we'll work it out. Let me remind you that we will upload the webinar to our YouTube channel and also to our website, so you can revisit it with more time. And also, if you want to discuss more thoroughly with Professor Segurado, feel free to send him an email. I don't know if you, Javier, wants to say anything else.
No, I just thank you, all of you, for attending, and I hope that you enjoy. And okay, then anything that you want to ask me personally, you can just write me an email. Of course, I'm open to that.
Okay, great. So thank you all the attendees for attending this webinar, and we'll see you in the next one. Goodbye, everybody.
Bye.